Welcome back. Today we're going to talk about load balancing and especially about dynamic load balancing. So this is lecture 9. I want to start with a couple of announcements about logistics. So Corey is still down, as you probably know. I just looked at the message of the day, and here's a little picture of it down here. It says the next update will be at 12 p.m. Pacific time, so noon. So what we'd like you to do is to turn in the written part of the homework, questions 1 through 10, as scheduled tonight at 9 p.m. And for the programming part, we will give you an extension on that. I encourage you to work on it on your laptop if possible. And if you're having trouble, please post questions on Piazza. There's some information both in the homework assignment, and I think some more information on Piazza, or certainly other students can probably help you. Ben and I can try to help you, especially Ben, if you have a configuration issue with one of a specific kind of operating system that you're running. But you should be able to do a lot of it there, and then hopefully once Corey comes back, you could just run some numbers on that. This is not a big there's a few different things we do ask you to run, but if you've got it set up, it shouldn't take too much time once Corey comes back. And we will announce a due date once it's back. So as a former nurse director, I will tell you that as soon as it went down on, when was that first time it went down? It was I guess Friday, because it was before the 72-hour window, which is when we say there's always an automatic extension. That's because I don't want to get phone calls in the middle of the night that Corey has just gone down, but as if you could call me. But anyway, but that's why we, just to relieve your anxiety, you'll know that there's always going to be an extension if Corey goes down within the last 72 hours of a homework being due. Now, what I noticed as soon as it went down is that there was a problem with the file system. So probably one of the most complicated parallel programs in terms of having to handle a complicated synchronization. You have both concurrent users accessing it, and it's parallel in the sense that it runs across a big parallel machine as the file system. And in my experience, when I was nurse director, it didn't matter whether you had a hardware problem, a software problem in the operating system, or something else. The file system was usually the thing that went down. And right now the message says that they're rebuilding it, I believe. It's in recovery mode. That probably means they're building something up from backup, and that can take quite a while. So anyway, I assume that they are, as you also know, Corey was down for scheduled maintenance last Wednesday, I believe it was, and most likely what happened is there's something in the quote upgrade that broke the operating system and then caused the file system to fall over. So that's where we're at, and we will just do our best. Hopefully it'll be back later today, and then you can wrap up. Hopefully you can finish your homework, but it is useful. Regardless of, even beyond this homework, to be able to run things on your laptop. And so I encourage you to do that. Do take the quiz survey if you haven't already done that. And also if you took it early on, like within the first day or so, we weren't collecting email addresses. So some of you answered you have a conflict, but didn't tell me what it was or who you were. So please do it again if you didn't provide an email. That would have been in about the first 24 hours. And by the way, if you provide your email, then even if you've answered it twice, we can figure that out. Most likely, there are problems with every other day that week that we looked at. So most likely we'll keep the quiz time, but we will try to make sure those of you who have a midterm immediately after it have a little bit of a break. So anyway, that's why we want to make sure we know what everybody's conflicts are. Okay, on to the topic of today's lecture. Any questions about logistics? I talked before about, some of the steps you go through in parallelizing a program. You have to identify the parallel work. You have to make sure there's not too much overhead in the parallelism. You have to make sure you've got good load balance across the processors of the work. You worry about communication, locality, and synchronization. We talked last time about synchronization. And today we're really going to focus especially on the first 3 of these, especially the third one, which is load balancing. So let's go back to the problem you're actually working on in the homework assignment that was originally due tonight. And that was dense matrix vector multiplication. I like to draw the picture like this because the X vector that you're multiplying, so this is A, sorry, I didn't mark A, multiplied times X is equal, Y is equal to A times X, and or plus equals, depending on exactly how we've specified it. Each one of these elements of X is going to be needed by this column underneath it in the A vector. So you can think of it as doing a broadcast of that element down, or you can think of it as doing dot products across the rows. Both of those things are happening. And in this case, this is a nicely load balanced problem in the sense that all rows have an equal cost. So it's a, and you are testing some things in terms of load balancing by trying different OpenMP schedulers. Now in matrix multiplication, which we aren't asking you to do, I like to think of it as the three-dimensional iteration space here. So we've got our C matrix, say, on the top, and we've got our A matrix on the front and the B matrix on the side. What does this mean? We've got our I, our J, let's see. So the I and J loops would be these two, the way I've drawn it. And then the K loop would be the vertical one. So a typical way to parallelize this would be to use what we sometimes call the owner computes rule, sometimes called domain decomposition. The owner computes rule says that you divide up the output and that whatever processor owns a chunk of that output is responsible for all the computation associated with that. So in this case, the output, which is the left-hand side, so this rule was developed for compilers that were trying to automatically parallelize things, but is also a good rule of thumb just to think about. We've got our C equals A times B here, or even if it's plus equals, that is the thing that's on the left-hand side is C. So if we divide C up, well, we can divide C up into, say, columns, or we could divide C up into rows. And then the thread that owns, say, a column of C would be responsible for all the computation of A. So it would need this piece of A times actually all of B. So it would take this vector and do a matrix vector multiply or vector matrix, and then you would and then you could compute each of these outputs of C. So that would be one way of doing it. So now you might want to think about what is the best, what is it better to divide it up by rows or to divide it by columns? So any comments on that in chat? Well, the thing to think about, the comment there is divided up by rows. Yep, we got it, and that's right. That's assuming that your C matrix is laid out in row major order. So if you want it, if it's laid out in row major order, that's probably the way you want to divide it up because those will be contiguous in memory. And even on a shared memory machine, such as what we're talking about right now in terms of programming with OpenMP, the problem is if you divided it up by columns like this, and remember this C matrix is being written by each one of the processors. So you don't have a problem with locking because each processor owns a different column of the matrix, but you're going to have false sharing here because you're going to have say a cache line that runs this way, and then you're going to have updates that run this way. And by the way, your cache utilization will be poor, all kinds of things will be poor. But just from a parallelism standpoint, you're going to have false sharing because that cache line, that one cache line that's here is going to be needed to be updated by multiple processors. Okay, so and why do we, by the way, why do we divide the output rather than dividing the input? And it turns out in matrix multiply, you can actually do this in a number of different ways. The nice thing in general about dividing up the output is we don't need to worry then about races, because if only one processor is responsible for all of the updates to that piece of the output data structure, and that's true whether it's a matrix or it's a tree or anything else, some kind of a more complicated graph or hash table or something like that. If only one processor is ever doing any updates to that thing, then you don't need to worry about synchronizing it, assuming they're not also reading it, which gets into a different issue. But in matrix multiply, it reads and writes the same piece of it. Now, you could also organize it by blocks, and that's actually probably a better way to do it for matrix multiply. And that would be for the same sorts of reasons that you saw in cache optimizing it for serial code, which is you want, you're going to get a much more reuse. So you can sort of see that by the surface to volume ratio here. These do not have, these have more surface, which means you're reading that B matrix, and unless you can fit that entire B matrix into the cache of one of your cores, you're going to be running through the B matrix multiple times when you, you're going to be running through the elements of, the A vector. So you're going to want to, the blocked algorithm will typically be will give you better performance. And that we'll revisit that when we get to distributed memory parallelism as well. What about something besides matrix multiply? We've done a lot of work with matrices, and one of the reasons we start with those is because not only is it an important kernel, but it also is fairly easy to parallelize and has some of the most dramatic impacts in terms of memory hierarchy optimizations. But let's say that we're doing something like implementing neural nets and we're implementing a convolution. Now, typically, by the way, the parallelism would probably happen even at a higher level, although it can also happen within a particular image, for example. So in a convolution, and we won't go through the details of what this means, but you can think of having, say, an image that looks like this that's got a white X in the middle of a black background. And I'm just representing that with bits. And we've got a convolution, which is a little pattern or kernel that's got a pattern that we're looking for. So in this particular convolutional kernel, we're looking for diagonals that go like this. And we slide this thing across the image and multiply the underlying pieces of it and use that to compute a value at the center of this, which will, and so for example, you'll see then you'll get a high number when this pattern matches the underlying image. So the point of that is just, without, as I said, trying to go into details, that this computational pattern, which comes up all over the place in scientific computing and comes up here in convolutions, is that you're sort of sliding through this, in this case, two-dimensional array. We can also do it in 3 dimensions, but in this case, a 2-dimensional array, and you're computing some kind of sort of an average with the including the kernel in order to compute one of the values of the output. And so this is sliding over like this. So what do we do in this case to parallelize this? Well, we can use the same approach of owner computes, and we can divide up the output data structure, which is this green region, into things. And we can also divide it up by rows. We can divide it up by columns. Probably don't want to do columns for the same reason that we talked about with matrices, but we can also divide it up into blocks, which is probably a better thing to do in this case because, and in this case, even unlike matrix multiply, you need the neighboring values above and below you, and for at least down here in this case. So if you've divided this thing up into, say, square blocks, this will also get divided up kind of naturally in the cache hierarchy into these square blocks. There's a little bit of this that will be needed by, say, in the middle here, that will be needed by 2 processors, but that's okay. This thing is read-only, only the green part is being written. By doing it in 2 dimensions, when you go around the corner, hopefully that piece of the blue thing that used to be the bottom will now be in the middle, or if it used to be in the middle, it'll now be in the top. And so you'll get to reuse these things. Whereas if this is a big wide image and it doesn't, and the whole image, the whole row doesn't fit in cache, or 3 rows don't fit in cache, by the way, that's a very large image, then you could run out of, you might have to go and read these all again when you go kind of around the corner. So any questions about that? So you can see that when we divide up work here, we do worry about load balancing. We're trying to get equal amounts of work sort of implicitly in this, but we're also trying to think about locality a bit. Mandelbrot set is an interesting one, and I showed this code before, and I'm not going to talk about it again today, except to say that this function, Mandel, which is being used on every output pixel of the image, they're all independently, remember this was an embarrassingly parallel problem, so at every point in here we're going to call this function, and without reading through the details of it, you should notice this while loop here. So this while loop goes from n, starts at 0 and goes up to max iters minus 1 in the highest case, but it also stops early if this value, the square root of these, is less than t, some other threshold that we have input. And so this should make you a little bit nervous about the idea of just dividing this up into equal pieces, because not every one of these points is going to have the same cost. And in fact, that's what happens if you execute this. If you try to load balance it by dividing up statically, you'll find that it doesn't get very good performance. On my 8-core laptop machine, I think in a static load balance, I got a speed of a little over 2. Whereas if I do something a little more dynamic, which is what I'm going to be talking about, I got a speed up of over 7. So definitely a big difference. One other example. So in that case, what we're seeing is sort of a fixed amount of data, a very regular data structure that we're computing on. It's a 2-dimensional array. It doesn't get much easier than that. We can divide it up into rows or columns or blocks. And in this case, it doesn't, the locality doesn't really matter because each point only uses that point. And so it doesn't do a +1 or -1. And so it's okay. We probably don't want to divide it up by columns because we're going to still have this be sort of running through the cache in the wrong way, but we don't really need the row above and below us. So this works just fine from a locality standpoint, but maybe not from a load balancing standpoint if we do it. And that's because the amount of work in each one of those cells is different. Now, a different problem that comes up, which also requires that we think of something dynamically, is a problem that you studied and I think did a project on in a 61B, at least if you took it from Professor Hilfinger. There was a game tree search, I forget what it was called, but anyway, where you're searching through this tree of possible moves. So it wasn't a physical tree data structure, this also can come up if you're doing say a search, a depth first search on a binary tree or some other shaped tree, a B tree or whatever. But what happens in game tree search is the kind of logical tree unfolds dynamically through the recursion. And you don't really know how deep the tree is going to be. You may know that there's a maximum number of moves in a particular game. That's not true for, say, the game of chess, but it may be true for certain games where you're, say, putting a piece on a board and the board will eventually fill up. So if you're adding something every time. But in either case, and I believe in the tree search, the problem that you looked at, you had 2 players, and depending on what moves were being made, a certain part of your tree might become uninteresting and you wanted to cut it off. And the point here is that this tree, the shape of this tree is something you don't know until you execute it. And so you can't in advance decide, oh, I'm going to give this subtree to one processor and this other subtree to another processor, and that will give you a good load balance. You're really going to need to do something dynamic. Any questions about that? So 2 cases that really came up that were somewhat separate. One is where we don't know how much work is at each point, but there's sort of an equal number. We know how many points there are going to be or how many data elements we're going to compute on. And this one, we really don't even know how many nodes in the tree, how many vertices the tree is going to have. Okay. Looks like I misspelled number here, but anyway, so we talked about the cost, the variability that comes from the cost of the task, the number of tasks, and the structure of the task tree, or in general, a task graph. So we can have a situation where there's a task that is waiting for 2 parents or more parents to complete. And these all can cause load imbalance. So if you try to statically divide things up, you will often have uneven finish times. There is another source of load imbalance, and that is machine variability. This is one of the reasons that, for example, even on my laptop or on a machine like Cora, you will sometimes try to pin your threads to processors. The OpenMP runtime will try to do that for you. This comes up if you're using a cloud system in which the nodes in the cloud computer are being shared by other users. And so if some of them come in and use the processor, it may slow down one of your nodes or one of your cores, even if it's knocked off the thread that was executing on that core doesn't execute as frequently because it's being shared by some other job. And there's a whole bunch of other things, like the operating system, by the way, can come in and run on one of your processors, and that can also cause the appearance of, can cause load imbalance. Okay, so these are some of the reasons that we need to worry about load imbalance. I mean, we need to worry about it even if we have a nice, quiet machine that doesn't have much variability, and we have a nice problem such as matrix vector multiply, which is what you're looking at now, because you still have to worry about things like the when the work doesn't evenly divide by the number of processors. But that's still a static load balancing problem. So in static load balancing, we divide the work into equal sized parts. So for example, if you know the problem size, or the matrix dimensions or whatever, you can do this in a very straightforward way, divided by P. And the only thing you have to worry about here is the round off problem. That is, what happens with that extra chunk of work if it's not evenly divisible, and you want to make sure that it gets divided evenly over the processors and not all clumped on one processor. Okay, so but if we have static static scheduling and we've got this equal amount of work, we'll start with this easy case here just to have a picture of what it looks like. Let's say we've got 30 iterations of a loop. They all take the same amount of time, so their distance here, the width of them is all the same. This is serial time running in this direction, and we want to run them on 2 processors. Well, we could say something like pragma OpenMP 4 on the for loop of this and schedule it statically with a chunk size of 5. And that would divide my iterations up into chunks of size 5, and 3 chunks would run on each one of the processors, and you would get a perfectly even finishing time. And you can see even in this case how that chunk size might affect sort of how even it is if it's not a multiple. I picked something that was that divided into 30, so that it would give you nice even finish times. Okay, but what happens if the cost per iteration is not equal? And this, kind of looks like this sort of telescoping thing here. Maybe the opposite of a telescope is going out the other direction. So the tasks start out being really expensive, and later towards the end, they start getting cheaper and cheaper. And so this is not unusual. I mean, one thing that might give you something like this could be a tree of some kind where you've got fairly heavyweight tasks at the top. If you've got a problem, if you're doing something like Gaussian elimination on a matrix, and you're starting at the top of the upper left of the matrix, as you work through it, you're kind of working on the whole matrix, and that piece of the matrix shrinks as you go through the matrix, and so the cost of each one of those tasks can shrink over time. So we can still try to schedule this statically and give our chunk size of 5. Not too bad. It gives us a close to even finish time, and this by dividing it up into 5 is probably better than dividing it up into, say, chunks of size 15, which would have put all of the big chunks on the first processor and all the little chunks on the second processor. So given that this pattern is somewhat common, it's probably a better idea to divide it up into small chunks. We can also just make the chunk size equal to 1, and that has an advantage of most likely giving you the closest even finish time, but can cause some additional overhead of doing the scheduling, which you're seeing. So, let's see, we can also, but we could also have a pattern of work in which the fast tasks, if you will, are distributed throughout the running time of the serial program. They're not all at the end as they were in the previous example. And now this is a particularly bad schedule, this static schedule with a clump size of 5, because it just turns out that all of these chunks are every other one. The big ones are here and the little ones are there. So we get a very uneven finish time, and we have poor load balance in that case because this processor is going to be idle while it's waiting for the other processor to finish. Okay, so one of the things that we can do if we know what the estimated cost of each of these tasks is. So let's say that we had a number that was basically the width of this cost, the width of the task, which is the cost of it in terms of running time. So if we knew in advance that we had 30 iterations and we knew that the first 5 were going to be slow, the second time 5 are going to be fast, the third 5 are going to be slow, and so on. What we can do is to add up the total amount of work that we need to do. So let's say that we assign some value to these, which is the cost. That is, let's say these are about twice the cost of these narrower ones. And so we add up the total amount of work in here, which might be more like 45 units, if you will, divide that by 2, and then divide the total number of iterations in half. So if we do it this way, then we will get an even load balance. And what you can see by this, if you look closely at this picture, is this middle chunk of 5 expensive tasks got divided in such a way that 4 of them are on the first processor and 1 of them is on the second processor. And on the other hand, this one has 2 groups of the small tasks and only 1 plus this extra piece of the larger, more expensive tasks. So you can add up all the work. If you've got an estimate, it doesn't have to be a perfect cost, because typically, as you've seen, certainly from all the homeworks you've done, that predicting exactly what the cost is going to be is very hard given caches and things like that. But you may be able to come up with an estimate of what the cost is. So an example, and then we can add up all those costs and divide it by the number of processors, worrying about the round off again here, but we'll have to distribute that somehow as evenly as possible over the processors. And if you've got some really big chunks in here, that can make it a little bit harder. Sometimes we'll also sort them so that we deal with the fact that if there's some really big tasks, we sort of round robin schedule them. We put the big ones, give every processor one of the biggest tasks, and then we start sending the smaller ones, the next largest group around in the opposite order, and that should give you a pretty even finish time as well. But this is still static scheduling. This is looking at the estimate of work you're going to do. Now it's still happening in the program at runtime. It's not like at compile time or when you're writing the program, you can necessarily say, give this processor, whatever this is, 16 blocks. I think it's not that, but anyway, however many blocks this is, because you don't know necessarily when you're thinking about the program how big these are going to be. You might, but you might not know until runtime. But if you can estimate it before you start the loop, then that can be a good thing to do. In this case, you might, depending on exactly which version of OpenMP you're using and things like that, I don't think any of them take in a vector that says exactly how many iterations each one of the chunks should take, but that's what you would want to do. So I would strip mine the loop, which we saw when we were doing tiling. That means take our loop and turn it into 2 nested loops. The outer one would just go over the chunks, and the inner one would go over the elements of each chunk. And the outer loop, those outermost loop, the number of elements in each chunk would vary, and you would have to keep track of that in your data structures. But then that outer loop would hopefully have the same amount of time, and it would be, you would divide that would be equal to the number of processors. So an example of where this kind of thing comes up, where you might be able to estimate the time, is if you have an array of arrays where the inner arrays have variable length. So you see this, for example, in Java. I think you may have used it in looking at something like how you represent a graph as a adjacency list representation, where you have an array of all of the vertices in the graph, and then an array or maybe a linked list that is the number of edges that are connected to that vertex in the graph. So that would be something where you may be able to estimate ahead of time how many vertices, how many edges each one of those vertices has, and therefore you can divide it up. That's, by the way, also what a sparse matrix looks like. If a matrix has mostly zeros in it, like it's over 99% zeros, oftentimes the best way to store that is not to store all those zeros, but to compress them out and only store the non-zeros. And so these would be examples of things where you know in advance roughly how expensive each one of the rows would be in a matrix vector multiply. And we will talk about that example a little bit later, of sparse matrix vector multiply. But anything where you have, say, an array of variable length arrays, but you know what their length is, then you can use this kind of load balancing. Okay, but what about the dynamic case where you really don't know until you're in the middle of the computation how expensive something is going to be? So you're running a loop. You've got something like that while loop in the Mandelbrot, or you're looking at a tree and you don't know how big the total cost of one of the subtrees is going to be because you don't know how many children are below it. Maybe the cost of each internal node is the same, but maybe the leaves are different, things like that. So we really don't know what the costs are going to be And so you can't really look at it and say, okay, well, at runtime, I'm going to figure out what the total cost is going to be of everything, maybe sort them or whatever, and divide up the work roughly evenly over the processors. So the question is, what is an example of something where you can estimate the amount of work, and how do we estimate the amount of work through something like loop lengths? Yes, so the example that I gave on the previous slide where you have an array of arrays, and the outermost array, we'll think of that as n, those are the n elements that you want to operate on. You're going to parallelize over that loop of n things, but the length of each of the internal arrays is different. You can then, that would be something where you can estimate, assuming that the cost is linear in the size of that inner array, you can estimate the cost of each one of those relative to each other at least. And so then you can figure out how to load balance it because you know their relative cost. Another thing might be if you have a function that says that is somehow based on, you're doing a matrix operation and you know the dimensions of the matrix, things like that, you'll know what the estimated cost, say an order n cubed algorithm, not a perfect estimate as I said, but nevertheless something where it would typically be, because it's based on size of something, that there's some data structure in there that will affect the running time. Okay, but in cases like game trees, or in the Mandelbrot case, we don't know when Mandelbrot, until we run it, we don't really know when it's going to stop early and stuff like that in that inner loop. And similarly with game trees, you don't know where the bushy part of the tree is going to be until you play the game. So in this case, we use dynamic scheduling algorithms, and one of the earliest papers on this that really identified it, and other people had used it before, but in this paper, Tang and Yu really worked out the theory behind it, and sort of, well, kind of laid out what this whole idea is they called it self-scheduling. So when you hear the term self-scheduling, and that will come up in OpenMP, it is one of the types of scheduling that you're using actually even on in the homework, would be, when it says dynamic, would be a self-scheduling algorithm. So what happens in this case is you've got a shared queue of all the tasks to do. So let's say that we are working on something like a loop. So all of the iterations of a loop can be put in a queue. And that could just mean that you put the index I from 0 up to n-1 as elements of this queue, and then there's some other data structure that you're actually operating on. And when a worker needs something to do, so the workers are the processors now, it will go and get the next index out of the queue, some value between 0 and n-1, and it will perform the work that's on that. And in this particular case, I'm assuming that the cost of each of these tasks is not the same. And so it didn't make sense to just divide this up into n over p pieces. So this worker, for example, and this worker might finish quickly and then go back and get more work from the queue. So you're just using this queue in order to share all of the work, and the tasks are being, if you're doing something like a loop and you know in advance what all the iterations are of the loop, you could just stick them all into the task queue. If you're doing something like a game tree search where you don't know what the tasks are until you're in the middle of the execution, then a particular worker, when it spawns some children, will put those into the task queue. Okay, any questions? Okay, so that's the idea of self-scheduling. Now, we almost immediately, as soon as we have a scheduling problem like this, have to worry about the overhead of the scheduler. And in this case in particular, we've got this shared data structure. And by the way, this will be something you'll be working on in homework 5. You're looking at a shared data structure, and all of these workers are trying to access this. So you can imagine the easiest way to implement this is to take your queue code, or maybe you want a priority queue for some reason, but you've got your code that's in, you wrote in, say, 61B for a data structure like this. You just stick a lock around the whole thing. Well, if that's the case and you have fairly small amounts of work here, you're going to have a lot of contention. You're going to be bottlenecked on this task queue access. And so the next idea that comes up, and it was developed especially for compilers that were looking at loops, so iterations of, from 0 up to n-1, was to put to grab a set of iterations rather than a single iteration. So this is called chunk scheduling, and we kind of already talked about it before in the static case, but in this case, you can also use it for self-scheduling. So you're still putting individual tasks, let's say a loop index in here that says this is the task associated with the ith iteration of the loop. But when I pull out work, I might pull out 5 things rather than pulling out 1. And you can specify that in the, say in the OpenMP interface. So the advantage of this kind of a chunking is that it reduces the contention, the frequency with which you're acquiring the lock and releasing the lock, and therefore will reduce the contention on the task queue data structure itself. And so in this case, the iterations can still have variable cost, and in this task queue, in both of these cases with self-scheduling and with chunk self-scheduling, you can, it should even the load balance as long as you don't make your chunks too large. So you have this trade-off, which is if you make the chunks too large, and I think this is, yes, the next slide, if you make your chunks too large, then you can have an uneven finish time, even if you're doing self-scheduling. That is, even if you're doing dynamic scheduling, you've put all these tasks, so these, say, 15 tasks into a queue, but you've set your chunk size to 5, then you might have a pretty big uneven finish time here and a lot of load imbalance. So this isn't a lot of idle time, which is the way you see load imbalance as a processor that's idle. So smaller chunks will typically give you a much more even finish time. So in this case, if our chunk size is 2, we will get an even finish time. There is 1 task left over because there were an odd number of tasks in this case. There were 15 and we have 2 processors. So it's a little bit of unevenness here, but it's really as much as you can do if you've got 15 iterations to schedule on 2 processors. So how does this differ from the static scheduling? Well, this picture doesn't make it clear, but what's happened is I've actually stuck all 15 of these tasks into my task queue, and then when I'm pulling them out, a processor, in this case we just have 2 processors, pulls out a set of 5 chunks. And pulling out 5 chunks means I don't have to go to the task queue as frequently, so it reduces the contention than if I just had a task size, a chunk size equal to 1. I would sort of be bashing on my queue a lot. So if so I would have the chunk size would be larger than I avoid that, but I can still get an uneven finish time. So in terms of the actual schedule, this may be also what you would get in a static schedule of this particular problem. These also could have variable amounts of work. As I've drawn it here, they look like they have equal amounts of work. But it's still the case if they have variable amounts of work that larger chunks are going to lower the contention and the overhead of scheduling. You've got a function call, you've got to call the dequeue operation at the very least, you've got a lock probably somewhere in there. You're going to be trying to put your locks not around the whole thing. So you have to be a little bit more clever about how you implement your queue. Smaller chunks are going to give you a much more even finish time, even if these have variable size weights. Okay. So the last of these variations on self-scheduling that we'll talk about, and by the way, there are more, is called guided self-scheduling. And this one is also implemented in OpenMP, or is provided as one of the basic ideas. And it's really getting at this trade-off. The trade-off being that a large chunk size gives you low overhead, low contention on your task queue. The small chunk size gives you even finish time. So what they do in guided self-scheduling is they start with large chunks at the beginning, and as you execute, as you get closer and closer to running out of total tasks, then you start shrinking the tasks, the chunk size, so that you leave some other work for the other processors to do. So how does this work? Well, you're going to compute your chunk size k sub I to be the ceiling of and this is to deal with when it's not divisible, the total number of tasks that are currently left in the queue divided by the number of processors. So imagine that we've got, let's say, our 100 iterations and we've got 10 processors. So let me just make sure I didn't just do this. No. Then we will, then the very first processor who actually gets the lock on the task queue is going to look at the queue and say, oh, there's 100 things in the queue. There's 10 of us working on it. I will take 10 out of the queue. And that may happen for a little while until this this fraction drops to below 1, and so then when you below 10, and then you'll be only taking 9 of them out and 8 of them out and so on, and so that will leave more tasks in case, for example, in case the cost of these tasks is actually not equal. Right? So that first worker is getting a lot of work to do, but then after that, they're getting less work to do. And that way, even if that first worker, it turns out they got a big chunk of work, they got 10 tasks, but let's say they're all really fast tasks, then they can go back and get more work later that others have left. Okay, so let's see. So let me just make sure guided self-scheduling, it's just, it's starting with big tasks and it's moving on to smaller tasks to basically balance between the overhead and contention on the one hand and the in the even finish time on the other hand. Any questions about guided self-scheduling? Now, it turns out none of these papers are actually from Berkeley. There is another paper on an algorithm called TAPER, which even takes into account some information about the variability of the task, and there's a bunch of other algorithms in this space, but these are probably the 3 most important ones. And the question is, does guided self-scheduling have a pretty bad worst case scenario? All of these, you can have really bad scenarios. You can contrive even for the case where you're taking only one task out at a time. You can, if you've got variable task times and your first task is huge, then you can have that, but that would be the best you can do, is to wait for that one processor to finish that one big task. But you're right that if the first 10 things, and I guess we had a picture of this earlier, happen to be all really expensive things to do, and then the later ones are all inexpensive, that would be a bad idea to take 10 of them out on the first step, because they may, if they're the most expensive things to do. Okay, so the next thing that we do to avoid this contention problem is a trick that we talked about early when I first talked about OpenMP and how to parallelize a loop automatically, and that is to privatize the queue. So in that case, we were, for example, if we've got a variable that we're updating, we're just computing a sum or adding to it. We're doing a read and then a plus and then an add and then a write. Then we can make a separate copy of it, and everybody can work independently, and then you can do a reduction or add them together at the end. So there's various ways. And so what we are doing in this case is taking a private version of the data structure. So this may seem a little counterintuitive, but it turns out that often, even on shared memory machines like this, the best thing to do is to have a task queue that's only access that's private to a particular, I shouldn't really say private, that is kind of mostly owned by one of the processors. And so it's really distributed, if you will, across the queues. We're going to lose our strict ordering properties here on the queue if we were doing a FIFO queue before, because now each processor can access a different one of the queues, and that'll sort of reorder the tasks. So it has to be the case that is not important, that you don't care about exactly the order that you're going to execute these. But we're already parallelizing this loop, so presumably you didn't care too much about the task order. Okay, so we've got these separate queues. Now, clearly, if we just, we can take if we've got a fixed loop like that we're iterating over, we can take a chunk of tasks and put them into each processor's task queue. But the idea is that when they run out of work, they're going to steal from another queue. And so that looks like this, that if this processor P1 runs out of work to do, it'll go and find another queue. It'll look in the other queues until it finds some other work to do and move one of the tasks over, and then execute that task for the other processor. And so, but mostly you operate it out of your local queue. So what this should tell you is you still have to synchronize these queues. You can't do this without some kind of locking or synchronization. or atomics or something in order to make the queues work correctly, because at some point, in this case, P1 is going to go and access Pn-1's queue. So that queue has got to be protected by locks, but most of the time you're going to be executing locally, putting things in and out of the queue on your own processor, assuming you have plenty of work to do, and therefore, and nobody else is trying to steal from you. If everybody's got plenty of work to do, they'll all operate locally, and that avoids also the contention on the lock. So the point of this was to kind of split those up. So now you've got multiple locks, one on each one of these, or even if you have like just one lock per queue across over the whole thing, you have avoided the contention by reducing the chance that two processors are going to be trying to modify the same queue at the same point of time. Okay, so we'll steal from, we can do this sort of work stealing or task stealing, and we, how many tasks are you going to steal? Well, we can go back to the static scheduling, or we can go back to guided self-scheduling and say probably we don't want to steal a single task if a single task means a single loop iteration, for example. By the way, we can use this idea in a tree search, although we may want to sort of get the top of the tree distributed out into the queues, because otherwise it can take a while for the processors to find out which queue has the work to do. So how many tasks we may want to have a chunk. So you may want to parameterize the stealing algorithm by a chunk size as well. And which processor are you going to steal from? And so the question is, what is a task in this scenario? Yeah, so and just to be clear, because I have both rectangular tasks and circular tasks. So when they're sitting here in the queue, there are these rectangles. And then when I've moved it over here, I've moved over a circular. So the circles and the rectangles are, the orange things are all tasks. But I think this was asking a more general question about, is it is a certain block in the matrix multiply example? It could be, yes, it could be, or is it a designated piece of the output? It could be both of those things. So, excuse me, if you think about your matrix multiply example, if you've divided your C matrix up into, say, square chunks, I've got a nice square matrix that's evenly divisible, and you've got a square power of 2, a square number of processors, sorry, then you can, then each one of the tasks could be some of the work associated with that one of those output tasks. And it could be that the work is actually just all the work associated with this. So let's say that we have 9 processors, and we've got a dense matrix multiply that we're doing. We could divide the C matrix up into 3 by 3 chunks. Now for matrix multiply, dense matrix multiply static scheduling is going to be just fine. If that were a sparse matrix and a lot of those elements of the matrix were 0 and we actually compressed it so they have variable length, then such a schedule might not be the right thing to do. You could still have a chunk of work, which we could still divide it into those 9 chunks to give each processor one of them. But if we're worried about the fact that some of those chunks have a whole bunch of non-zeros, a whole bunch of work associated with them, and others do not, what we could do is divide it into smaller chunks. So let's say that we divide it into 81 chunks, so 9 by 9 chunks instead of dividing into 9 chunks. And we could initially give each processor 9 chunks. If we've got 9 processors, that's what I had, right? I had 9 processors. So we could give each one of them 9 chunks each. So the total 81 chunks get divided out. Each one of those chunks is a piece of the C matrix that needs to be fully computed. So no race conditions, the way we divided it up. And then, but if my chunk happens to be really fast because all of the A's and B's happen to be zeros or whatever, then I can go and grab somebody else's chunk if they're still busy working on it. And a task could also be a node in the tree in like game tree search. And you can go and steal a subtree basically of game tree search, something like that. Okay, so which one do you want to steal? Well, the first thing to notice, and I get a little confused here because of the way stacks and queues grow at different universities. They grow up or down. I think we at Berkeley grow our stacks down in 61B. Is that true? Do stacks grow down in 61B or do they grow up? At MIT they grew up, but anyway. So whatever they're doing, you want to, when you're taking tasks from your own queue, you want to treat it like a stack. That is a last in, first out. So you're going to take the newest thing, the thing that was most recently put on the stack, and execute that. Anybody know why? Well, the reason you're going to want to do that is gives you better locality. Because if you have any difference in locality between your tasks, that is, they're using some data that's nearby, then the most recent thing you're going to put on there is going to be the thing that has the best locality is going to be the thing you just put on there. You can think about that also in the task tree. And by the way, I'm not quite done. I think we'll just go ahead and I'm going to keep going in this lecture today. And if you need to go off to another class, you can go ahead and watch the lecture a little bit later. We should wrap up in about 5 or 10 minutes. So from a locality standpoint, I typically want to grab the thing that I just put on the queue because it might have some related data. It's just a heuristic. It's not always the case. They may be completely unrelated. On the other hand, if I steal, I typically want to steal from a FIFO queue. That is, I want to steal from the other end. And that's because I want to steal something that is the largest amount of work. It's older, it's an older task, it's been in there the longest period of time. Think about a game tree search or some other kind of tree search. I'm going to be stealing something that's higher up in the tree. Now that thing high up in the tree could have no children, so it could be a really cheap thing to do, which would make it a lot of work to go and steal, but it may be that it's more likely that something near the top of the tree is going to have a bunch of sub-children and therefore if you're going to go to the trouble of stealing something, you want to steal a kind of a substantial chunk of work. Again, because then once you get it locally, maybe you've got some locality you can take advantage of. So the last thing is the question of which processor should you steal from? Well, the first rule is you don't want to go to the same processor every time. Now, if you're doing game tree search and you're sticking the root of the tree on processor 0, then everybody better check 0 to get some work in order to get started. As I said, you might want to distribute the work around a little bit to avoid that kind of a bottleneck at root 0, but in general, you don't want to go to the same processor you went to the last time because they're more likely to be out of work because you just stole from them. Now, given that rule, that just means you need to remember who you stole from so that you are choosing a different one each time. You have some way of keeping track of that. And then you also, though, the question is, do you want to steal from a nearest neighbor or do you want to steal from somebody that's far away from you? Well, if you've divided things up in a sort of local way, it may be that your neighbors have also some locality. This depends entirely on the problem that you're working on. But things far away may be better for load balance because if you've got a bunch of processors that have all run out of work and they're all stealing from each other, then it's kind of like a hash table with lots of collisions in it. They're just not going to find any more work. So they want to jump far away in order to get to find a processor that has not run out of work. And you are not responsible certainly for the proof of this or even the details of this, but I did want to give you this theoretical result that underlies a lot the scheduling algorithms in here. When you're doing work stealing, it turns out the best thing to do, at least with provable high probability, and this is ignoring locality considerations, is to steal from a random processor. So each time you compute a random number and you steal from a random processor, most likely that will not be the processor you just stole from. And it turns out you can prove a property taking into account randomness that is close to optimal to do that. And so formally what it says is that with high probability, if the number of tasks n is greater than p log p, so you've got kind of at least log p things per processor if you divided it evenly, then the amount of load in each one of these bins. So we're now thinking about each bin as a processor, and each task is a ball that we're throwing into the bins. If we're sort of throwing these balls into these bins randomly, we're going to get something that's n over p, which is the best we could possibly do, plus this kind of complicated looking factor, but it's not too big, right? It's got an n log p over p inside of here. And by the way, it's kind of bad if n is only equal to p. In that case, you can end up with much worse load balancing. And to me, that's one of the things that you take out of this theory, is that in general, you want to have enough tasks. That p log p is probably a good number of tasks to have. If you've got only, like you've got P+1 or P+3 or even 2P tasks. That's probably not enough tasks to keep, if you're trying to do work stealing, to keep all of the processors busy. But if you've got log P of them per processor, that'll probably give you much better load balance. And there's some theory to back that up. And there's a question, could we pass in some sort of function that selects which thread to steal from based on the type of problem we're solving? Absolutely. If you know something about the domain of the problem you're solving, let's say you're solving a sparse linear algebra problem and you know that there's a certain property of the matrix that all the non-zeros are clustered around the diagonal, or you know that it's you've got a histogram or something like that, you've got some estimates of the cost, you absolutely could put those in. And so, for example, rather than having a regular FIFO-LIFO queue, which is treating the local queue like a stack and treating the remote one like a FIFO queue, you could use a priority queue. And then you could execute, when you steal something, at least from the purposes of stealing, you could try to always steal the largest task, largest estimated task cost. And so there's lots and lots of information you can, and also when it comes to locality, dynamic load balancing is usually basically an approach of last resort. If I have no other information that I can use, I'll start randomly throwing tasks around the machine. But if I've got some other locality information or some other cost estimates, it's usually going to be better to use those. Also not responsible for all this, but I'm just pointing out that there's lots and lots of papers on how all these different algorithms work. And I've talked about a few of these in here, but there's more, and I forgot to put the citation, but I'll add that to the slide. This came from somebody else's tutorial on load balancing. So when you're load balancing independent tasks, one thing to think about in terms of how hard it is, and hard is a kind of a funny word here, if I've got some loop and all of the statements inside the loop have either there are other loops that have fixed bounds and there's no conditionals inside of these that are going to vary the workload. Now you can have conditionals, but if the conditionals have the same amount of work on each branch, you're okay. If they have very different amounts of work on each branch, or you've got something like a break statement or a while statement that has some data dependent termination of the iteration of the loop, then you're not going to be in an easy case. So harder case is where you've got some variability, but you know, for example, what the cost is of each one of those tasks. So we talked about that one. You can do things like sort it. So for example, maybe you've got an iteration that's going over a bunch of images, but the images have different sizes, but you can read in an array of all the sizes, then you can figure out how to load balance that kind of offline, that is before you start the actual computation, even though it's at runtime in the code. And the hardest case is where you've got these conditionals, you've got breaks, you've got loop bounds, exceptions, whatever, that are jumping out of the loop. That is going to make it very hard to load balance. And when you're in the hardest case, that's when you resort to work stealing and either certainly self-scheduling, but even some kind of work stealing with these distributed queues and things like that, because you just have no information about how long anything is going to take. We haven't taken into account the fact that some of these might have dependencies between them and some of them might have communication between them. So that's also application specific information that you may want to take into account. And there's a whole bunch of other load balancing algorithms that look at some of those issues. So just to kind of wrap up, if you've got a problem that has some load imbalance and you're trying to figure out in your application whether you've got a load balance problem or you've got some other kind of performance bottleneck, all you know is that you're not getting linear scaling or anywhere close to linear scaling. I'm running on 8 cores and I'm only getting a speed above 2. What's going on? Well, it could be that you've got very expensive synchronization, but perfect load balance. That would be the picture here. It could be that you've got poor load balance, and especially when you put synchronization, and this is showing barrier synchronization, remember, which is where all the threads wait for all the other threads to catch up, then you're going to have load balance. So all this idle time here, if you added it up and divided it by P, that would be your lack of perfect parallelism that you're getting, the amount of slowdown you're getting relative to perfect speed up. And the worst case, of course, is when you've got one really slow thread or one serial thread. Maybe you've got another barrier here, and this is really just one thread doing some amount of serial work, which is really an Amdahl's law bottleneck. And notice that also that if you don't have enough parallelism, then then, you know, for a particular, say, phase of the computation, you're going to have a whole bunch of idle time where only some of the processors are working. So all of those things can look like load imbalance, but they can't be fixed by work stealing or any other fancy load balancing algorithm if you simply don't have enough parallelism. But the last comment I wanted to make about this is when you're trying to find load imbalance, you want to make sure you're not just computing averages of running time across the processors. That's very common, and it's a fine thing to do when you're trying to figure out how fast your code is going. But at some point, you want to make sure you're actually computing the actual values of each of these things and figuring out, because if you're computing an average, it'll blur all this together and it'll make it very confusing. If you compute a max of all these, you'll have no idea that there's a bunch of load imbalance in here. So you really need to look at the individual, like the min and the max can be an important thing to look at here. So you'll at least have a sense that there's some load imbalance. And there's just sort of a summary of kind of what I said on the previous slide. Amdahl's law can cause problems. Insufficient parallelism can cause problems. Too much parallelism overhead. If you've got a nicely load balanced task queue, but you're spending all of your time beating on a shared queue, you're going to not perform well. And we didn't really talk about locality very much, just a little bit, but that also, and in general, what we'll find is there's often a trade-off between your load balance and your locality. And here's one simple way to think about that, which is if all I cared about was locality, I would just let one core do all of the work, one processor do all of the work. It's got all the data there and it can optimize for locality. If I optimize for load balance, I want to spread everything out as much as possible. And so we'll find in practice that these two things will often conflict with each other in less trivial sort of scenarios. And then finally, this load balancing problem. And I'll just mention, you know, we've talked a lot about dense linear algebra. We've talked a bit about particle methods. And today I was in convolution, we were really looking at structured grids. These are all sort of the easy cases. And the cases where this variable work comes up are in some of these other things like graphs, hashing, sparse linear algebra, and so on. So any final questions? Okay, great. Apologies for going over, but thank you very much for staying. And we will see you on Wednesday, and we'll talk about shared data structures, like how you build things like these queues that you might use for load balancing.